If we continue and look at number 4, it's another multiple choice question, and it says that the height of a missile t seconds after it has been fired is given by the function h equals negative 4.9 t squared plus 44.1 t. Which of the following represents the number of seconds it will take for the rocket to reach its greatest height? So again, you launch a rocket in the air, it reaches a maximum height, and then it falls back to the earth. Let's graph it in Desmos and see what we get. I've got my output equals negative 4.9 times my input squared plus 44.1 times my input. And, oh, I gotta zoom way in from what we were doing in the last problem. So if I look, my rocket starts at 0, 0. It lands like 9 seconds later, which means that it has to reach its maximum height here at 4.5 seconds later. So 4.5 seconds in, we reach our maximum height. Number 5. There's a tour company that has a ticket price that goes down for $2 for every additional person who signs up for a group trip. They charge 52 minus 2n per person, where n is the number of people that go on the trip. Their total revenue as a function of the number of people who go on the trip is r equals negative 2n squared plus 52n. They want us to find out how many people maximize the revenue for the tour company, or where do I make the most money. Now I see that there's two equations here. The bottom one is what actually looks like my quadratic. The other one looks like a straight line. I believe when I graph them both, I should see, hey, where do they make money and where do they lose money? So if I graph them both, I'm really still just looking at the maximum number of people, or the maximum input, which is going to be the x value that gives me that highest point. So I'm going to take my revenue function, which was my output equals negative 2x squared plus 52x. So here's my revenue. And then if I look at what we charge people, minus 2x. And there's a straight line. So you can see that there's a couple places where maybe they won't make as much money. But again, I'm looking at my revenue function, which is the first one I had. And if there's 13 people, that's where I make the most money. When there's 13 people that show up. So 13 people maximizes my revenue at $338. Again, the people were the input. N was the number of people. So when I graphed in Desmos, X was the number of people. So looking at number 6, it says that the amount of cloth that is used to make 4 curtains is given by a function. You can read the function. It's right here. Where W is the width of one curtain and A is the area in square feet. It says find the width that maximizes the area of the curtains, then determine what the maximum area is. And so with that being said, again, W is the width, A is the total area. So I want the width that maximizes the area, and then I want the maximum area. So here's going to be my width, and then max area. And those are the two values. They should be my vertex when I graph this. So if I take a look at Desmos, I've got negative 4 times my input squared plus 40 times my input. Here's my graph. And it looks like if I have a width of 5, I get a maximum area of 100 feet. Because my input, or my x value, is 5. My output is my area, which is 100. So with a width of 5 feet, I get a maximum area of 100 square feet of curtain. So then if I make curtains with a width of 6 feet, I need to know the area, which means that I need to use the table function, because it's asking me for what happens at exactly 6. So we use settings, table, we input 6, and if I have a width of 6 feet, that means that I'm going to get an area of 96 square feet. So I get 96 square feet when I have a width of 6. Again, graph the equation, know what your inputs or x's are, know what your outputs or y values are, see what happens. If you take a look at number 7, it says that one of the games at a carnival is trying to ring a bell with a ball by hitting a level that propels the ball into the air. So think of like that strongman hammer thing. You swing the hammer, you hit this lever, and it knocks the ball all the way up, and you're trying to ring a bell. The height of the ball is modeled by h of t is equal to negative 16t squared plus 39t plus 2. Now this makes sense because the ball goes up, and then the ball goes back down. The specific question is that if the bell is 25 feet above the ground, will the ball hit it? So we need to take a look. First we need to graph our equation in Desmos, because I need to know the function for the ball. So I've got my output equals negative 16 times my input squared plus 39 times my input plus 2. And I can zoom in. And then here's the ball's height over time. So I can see that the ball starts at about 2 feet above the ground, and then it goes all the way up, and eventually it hits the ground. Now I need to know, will it hit the bell if the bell is 25 feet above ground? And if I take a look, or specifically if I graph y equals 25, I can see that the bell is 25 feet above the ground, and if it is, that means that I would have hit my ball, or the ball would have hit the bell and been able to bounce back down because of the fact that my maximum height for the ball is 25.766 feet, which is significantly higher than the bell. So what it's saying here is, if I make a sketch, I'm hitting the ball and it's going up, and then it's going to come back down. I model it by saying the ball goes up, the ball goes down. The bell is only 25 feet tall, which means that when I hit the ball, that ball is going to shoot up, hit the bell, and fall right back down. It's not traveling any horizontal distance because, again, my input is time, but I can simply say yes because the ball has a max height of 25.76 feet. And you already know that 25.76 is greater than 25. So there we go.